Hello, all you precious penguins out there. Welcome to another episode of A Little Greener, a podcast all about nature, conservation, and sustainability. I am one of your hosts, Casey, and I am joined by the wonderful Sarah. Sarah, how are you today?
Hello, I'm doing all right. I'm recovering from a headache last night. And I'm all like, it's the first day of my weekend, and I just get really annoyed when my weekend hits. But like last night, I couldn't do anything because I was just knocked out with a headache. And then you wake up and you still have it. I'm just like, this is fair.
Yeah, that lingering headache is no fun. I'm starting to get more headaches by being just, you look in the book and they're like, oh, yep, you're pregnant. That happens. And you're like, great. Another thing
Thanks.
that I didn't think about. Thank you. So I don't know what this has to do with the baby, but great, my head hurts. So I can sympathize a little bit, but yes, that's no fun and super frustrating. I am heading into vacation mode, so hopefully my brain woohoo is functioning. My cousin Ben, I saw him yesterday. Hi Ben, is an avid listener, and he was like, "Are you gonna do a live show with Sarah, the first in person podcast?" And I was like, probably not, friend. But
no, here two things. If we had more time, I would say yes.
Yeah.
But I only have the one night that I'll see you guys. And then two, I don't think our recording equipment is appropriate for
I
it.
have thought of the logistics of this, and no.
Yeah, it only works because we're in two different places. We would need like a different microphone setup and all of this. It would just be really bad sound quality. We could do it, but it would be bad.
I would just have to be in a separate room from Sarah.
Well, I mean, we could sit together and do
okay.
it, but the sound quality wouldn't be good. I don't think. I don't know that we would be able to use the microphone, or if we did, it would be anyway. So yeah, probably not. But I did think about it. It would be fun someday.
Someday we'll put it on the goals list.
Mm-hmm. But I am excited to see you. That will be fun. Looking forward to it. All right, Casey, I have a weird question for you today. I know we've talked about the true crime and stuff before, but how do you feel about mysteries? Are you somebody that enjoys a good mystery?
I like a mystery, but I like it to be solved at the end. Like, so for example, I love like Knives Out and Glass Onion and Death on the Nile we watched the other day. Like, I love a good mystery story. I like putting the pieces together and solving that kind of stuff. I don't like things like unsolved mysteries, like the show or like
that show used to scare the heck out of me.
Yeah, well, I like to like it's like and they disappeared and question mark. I like some resolution at the end of my mystery, but I do like the process of trying to solve it. So
yeah, I feel very similarly. I enjoy a good mystery. Knives Out and Glass Onion, I feel like they're sort of bringing back the mystery to mainstream pop culture. So I've enjoyed those. I just finished a book that I think I got from our friend Corinne from our former workplace. I think this was a book that she was giving away that I picked up, and it's a Lady Sherlock Holmes.
Oh, yes.
Mystery.
Yeah. I remember her reading
and
that.
So this was the first one in the series, and I have actually never read actual Sherlock Holmes. I should probably do that. But I did enjoy the book. I enjoyed the mystery. I like it when they give you the pieces so that you can put it together, which I don't really feel like this book did. But I do still like at the end when we get all of the pieces and get to put it together. It's a very satisfying thing. So this episode, we're going to be talking about the mystery of climate past. And this was inspired by your last episode, Casey. We took a look last week, if you haven't listened to that one yet, at some climate myths. We busted some climate myths. And I do think that knowing more about how we know what we know about the climate helps us to combat / navigate potential myths and misinformation that are out there. So that was one reason that got me thinking about that. And we also talked about some things last week, like you showed me, we can't really show the listeners, but we talked about a graph that goes back that talked about carbon dioxide in the atmosphere going back 800,000 years. And if you're listening to that, you might be like, what? We have not been around measuring carbon dioxide for that long. That is ridiculous. How can we possibly say that? So we're going to talk about that tonight. We are going to talk about how paleoclimatologists, what a awesome thing to be, what a cool name, how they kind of put together the mystery of the details of climate before we had recorded measurements. So stick around for that discussion. All right, so tonight we are going to be talking about a handful of things that scientists will use to put together information about climate, weather, carbon dioxide, those types of things, and to sort of put together a picture of what we know. But I want to start off, before we get into past data, how we actually know what we know about climate in our atmosphere today. And for as much as we talk about this, Casey, it is something that I know very little about. So starting with carbon dioxide, are you at all familiar with how we measure carbon dioxide in the atmosphere?
I'm gonna say we take a sample of the air.
Yes.
And then I don't know the particulars. I'm sure there's multiple ways too. I'm sure that there like you can like distill it in different ways, measure it by weight or microscopes or light or whatever, but I'm sure there's multiple ways to do it.
I'm sure there are.
Me.
Yeah, no, I'm sure there are multiple different ways. And to be quite honest, even after reading about it, I'm still like, all right,
if you say so.
Whatever you say. Yep, it's kind of like when we talked about nuclear fusion, and I was like, listen, I just feel like unless you've been in the room, unless you've seen these reactors, it's hard to sort of contextualize how it all works. So what I can tell you about recording carbon dioxide in the atmosphere is that it didn't start until the 1950s, specifically 1958. Back then, the carbon dioxide in the atmosphere was at about 315 parts per million, and we recorded this level at the Mauna Loa Observatory in Hawaii. So that is our longest running source of instrumentally measured carbon dioxide in the atmosphere, I guess you could say.
So I was curious why, like what prompted us to start measuring that? Like, is it just something that we were curious about if we were measuring everything? And it actually looks like the reason is on a NASA page, if you guys want to check it out, is because they knew that carbon dioxide being absorbed by the ocean made the ocean more acidic. And because there were a pair of papers coming out in the 1930s and 40s that argued that humans had increased the amount of carbon dioxide in the atmosphere. And so some people believed these people and some people did not. And so they decided we have to start measuring this. If people are going to start claiming, we need to know if that's even true. And so that's why they started looking at it.
Basically climate change research, and curious about the causes and the impacts was the reason this started. And you mentioned NASA. We talked about it last week too. NASA has a bunch of great information. So as always, there will be links to some pages in our show notes, but I did use a lot of NASA sites as well as our good friend NOAA, which I wrote down this time.
I'm proud of you.
The National Oceanic and Atmospheric Administration. Those two A's always get me, but they have a lot of great resources too. So you can find links to those in the show notes. So when we started recording carbon dioxide, that's sort of the when and the where. And at least one of the main techniques that we use now for getting these measurements is spectroscopy. Basically, we're shining infrared lights through samples of air and looking at the results. It's like the absorption pattern of light from different molecules. We talked about that a little bit when we talked about color in one of our previous episodes. So that's kind of what scientists are using to look at the composition of the atmosphere. We now measure carbon dioxide at several remote sites around the world, but they do also talk about how carbon dioxide is actually really well mixed into our atmosphere. So the readings from different sites tend to corroborate really well. And satellites, now we have satellites that have added to our ability to measure carbon dioxide. So you can find more about that on NASA's website as well. They actually have a page that you can go to that is just about monitoring carbon dioxide. You can track readings from their satellites like that are specifically that this is their purpose to look at carbon dioxide as well as other parts of our atmosphere and kind of track carbon sinks and things like that to just really give us a better idea of what is going on with our atmosphere. So you can track the latest measurements for carbon dioxide, which their latest measurement from January of 2023, we are now at 419 parts per million of carbon dioxide in our atmosphere. So up 100 parts per million from when we first started using instrumentation for recording. So that's kind of how we do it now for carbon dioxide. Regarding temperatures, according to NASA, we have lots of sources for measuring temperatures around the world, including more than 32,000 land weather stations, weather balloons, radar, ships and buoys, satellites, and volunteer weather watchers. So we have lots of sources for temperatures. Again, going off of what we talked about last week with climate myths, it's just another thing to look out for when you're looking at climate data or reading things about climate change. That can be another sticking point sometimes when people talk about temperatures. Sometimes they're talking about global averages. Sometimes they might be talking about a specific country. They might be talking about surface temperatures. They might be talking about ocean temperatures. So just another thing to double check and look out for as you're reading through information about temperature and climate. And then in terms of sort of modern recording, we started recording global temperatures around the year 1880. So we have a good amount of data here. Of course, the amount of data, the location that we're measuring from, the methods, accuracy, all of those things have improved over time. And there's some great information out there about how data and records are adjusted accordingly, which is also a potential source for some climate myths out there.
I feel like 32,000 weather stations almost feels too little for the preciseness of data that we get.
And I will be honest with you, I don't know if that's a global total.
Okay.
I don't know.
Just because like my phone can tell me what temperature it is and it pinpoints it to like my town. And then if I go to the next town over, it will pinpoint me to that town. I'm like, this is not even that different of a place, but it changes.
I also question how accurate some of the
fair enough.
I don't know where that information is coming from.
I do know that like but yeah, some of it's like AccuWeather, which aggregates a bunch of different like local sources, but super cool. I mean, weather has always been extremely relevant to human life. Like if you're on a boat, if you are growing crops, if you are trying to figure out how much to stock up for winter, all of this is very important. So it has been recorded by many different people in many different walks of life over time.
And what a spectacular lead-in, Casey, to how we got this information before we had these recorded measurements. So this is the next sort of group of things that we're going to talk about. This is referred to as proxy data in terms of climate. So these are things that we can use to give us a good idea of how things were when we don't actually have measurements for them, if that makes sense. And the first one that I want to talk about is historical data. So as you say, Casey, temperature, weather, climate is very important to us for lots of different reasons. And so it's been recorded for us in some different ways as well. Things like farmers' logs, travelers' diaries, newspapers, ship logs. I love this. This came from NOAA, this sort of summary of using historical data. And they gave an example where they said that scientists used historical grape harvest dates to reconstruct summer temperatures between April and September in Paris from 1370 to 1879, which is a very specific example, I feel like, but I enjoyed that very much.
Okay, I'm going to use some data from my cousin's bachelorette party when we went to a winery. different types of grapes are like specific to very specific regions in France and where we were in the Finger Lakes. So they were like, they knew what type of grape and then what it took to ripen them over the course of time, which makes the best wine. That's why it's relevant.
There you go. Yeah. So it's really important. And so it was recorded. And so now that's information that scientists can look at and take and record. I love this for a lot of different reasons. One of which is when they talk about using ship's logs. I don't know why in my brain that translates to pirates. And so then I'm just imagining this data being recorded in like the Captain Barbosa or like Gibbs voice from Pirates of the Caribbean. And that just brought me some joy. But also, I just feel like this is my type of gig, man. I just want to go through old diaries and records and just be like, oh, here's a mention of, whatever.
It snowed, so it was being really
under rainy.
This.
So I really enjoy that. I could get behind gathering some of that. This is a thing that I understand. Spectroscopy over my head. Gathering historical data. Yes, I'm all about it. So, but in spite of making light of it, this is actually a really important and I think a really cool way to start reconstructing past information.
Especially when we're talking about this in relation to climate, like we want to know further back than when humans were recording, but seeing as we're attributing climate change to human sources of carbon dioxide, having really specific, like year by year, date by date, all sorts of different location information available is important because that's the time period we're really looking at the biggest change.
For sure. And I do, it's important to note too that different types of proxy data are going to be useful in generating. So yes, obviously when we're talking about this type of historical data, that's only going to take us back so far. There are other types of proxy data that we'll use to go back even further. So, and I do just feel like this illustrates how relevant it is as well. So by using this data, it helps us to understand why it's so important that we know this and just how much weather and climate impact us as well. So that's one big one. This next one is probably the one, I don't know about you, Casey, but that I was most aware of. I don't want to use the word familiar with.
I agree, yes.
But this is the one that I probably heard of the most, and that is ice cores. So to get ice cores, scientists basically take a big drill. I feel like the best thing I can equate this to is if you think of like drilling for oil. We're talking about a like big machine here, not like a handheld drill.
And going real deep.
And going real deep, yes. And this a lot of this is done in most of our ice core data is coming from Greenland and Antarctica. So they'll take this big drill and take out big cylindrical chunks of ice going deep down into the ice. I was watching one video where they were talking to a scientist who works on this, and she was talking about, she gave an example of they drilled down and took out a core that was 364 meters and went back. So the layers in that ice core went back about 20,000 years, just to give you an example of sort of size and time frame. So, and then they can basically slice up this core as needed, do different types of tests to record different types of data. And then the video that I was watching also talked about how they will save some of that core for future records, basically, as well. So the way that this kind of works is ice sort of forms in layers. So ice cores have very, very specific layers for basically yearly. So each year's snowfall will kind of form a different layer in that ice core. So even just by looking at that, scientists can determine things like the amount of precipitation, but they can also take multiple ice cores from around an area, and then they can look at things like wind patterns from that, just from the layers in the ice core. So there's some just sort of more macro or visual data that you can get that way. And then in regards to carbon dioxide and climate change, what I think is so fascinating is that there's little tiny bubbles throughout these ice cores that are basically little preserved samples of the atmosphere at the time that that layer was formed.
Yeah, especially if there's snowfall. Think about how airy and light snowfall is. And so when it falls down, yeah, there's a lot of
Mhm.
air in there for us to capture.
Yeah, I don't know why that is just so fascinating. So it's just like they're little time capsules of the atmosphere. How cool is that? So they can just, again, sort of directly measure carbon dioxide from that. And then they will also look at oxygen isotopes as a proxy for temperature.
Oh,
So we
okay.
can, yeah, so we can get carbon dioxide, and then, you know, we talk about how far back temperature measurements can go. One of the things that we'll look at, and this will come up with a few different types of proxy data. So I do want to take a moment to talk about oxygen isotopes. Again, this was beyond me, so I'm going to give you just a little quick bit of information. I'll have a link to a couple of articles that explain it more in depth if you are so inclined. But basically what you need to know is that there are a couple of prominent isotopes of oxygen that we find in water. So when we're talking about this, we're actually talking about oxygen in seawater. So all oxygen atoms are going to have 8 protons, but the nucleus might contain 8, 9, or 10 neutrons. So that's what we're talking about when we're talking about isotopes, is that different number of neutrons. So what scientists are looking at in these samples is light oxygen, or oxygen 16, that has 8 protons and 8 neutrons. This is the most common isotope of oxygen, followed by much lesser amounts of heavy oxygen, or oxygen 18, that has 8 protons and 10 neutrons in their nucleus. These things behave differently with regards to evaporation, condensation, and precipitation. That's going to impact how much is found in water versus ice sheets, and temperature impacts the way that all of those processes take place. So by looking at the ratio of light versus heavy oxygen in these samples, and by having a much greater understanding than I do of how all of these things work, and comparing it to a global standard of the isotopes that are found at a certain level of seawater, they can actually use this as a proxy to determine how warm or cool it was at the given time in the ice core, which blows my mind.
Humans are so cool. Like, we
Right?
didn't just figure out that there were different types of isotopes of oxygen. We had to figure out what impacts it and what different levels would mean over the course of time. Wow. Wow, people. Good job.
Honestly, like that's what I feel like every time I look at all of this. Like, it's just incredible to me, the number of things that people had to think of to be able to put all of this information together.
I feel like I don't like mysteries enough for
Right?
to find all that. I mean, like, oh, cool. Mission accomplished. There are types of isotopes of oxygen, but man,
well,
yeah.
yeah, 100%. Like, I've talked about this before, but there's many reasons that I didn't go into research, and I don't have that. I would love to assist on a research project like this, but man, I do not want to be the one coming up with all that.
No, it's wild.
Yeah. So direct carbon dioxide measurements, looking at those oxygen isotopes. They'll look at like particulate matter, like dust that they find in these ice cores that can give information on volcanic activity in the past. So they're really careful about even, mishandling these samples can mess up readings. So it's all very sort of controlled, this whole process. And the oldest continuous ice core records to date extend 123,000 years in Greenland and 800,000 years in Antarctica. So that graph that we talked about last week went back 800,000 years. And that is why we are able to do that, is because of these ice core proxies. So it's really fascinating that long period of time, that 800,000 years in Antarctica, shows us 7 ice ages with alternating interglacial warm periods, such as the one that we're living in today. So it's pretty cool. However, if you're listening to this and if you are thinking like a good scientist, you should be going, okay, but how do we know? Like, are you really going to tell me that these readings from these little tiny bubbles trapped in ice cores of carbon dioxide are as accurate as measurements that we're taking from satellites today? Like, how do we know that this information going back hundreds of thousands of years is accurate? And so one of the things that we can do for carbon dioxide is we can actually match that up. Now we have this overlapping period where we have information from these ice cores and we have our recorded measurements. So the British Antarctic survey has some good graphs and there where they show the overlap between ice core readings and instrumental records of both carbon dioxide and methane. And man, they line up really well. So that was the first time I'd seen that graph. I thought that was pretty cool.
Yeah. The fact that it lines up with what we know humans have been putting together, that's great.
Yeah, pretty cool. Pretty impressive. The next one that we're going to talk about, probably the one that I was the second most familiar with, which is coral. It is another proxy that we will use. And similar to those ice cores having layers is going to be a common thing throughout all of these proxy data. So coral, as coral grows, they actually add layers to their quote unquote skeleton of calcium carbonate. They're basically absorbing things in from the water as they are growing these new layers of calcium carbonate. And the things that they have access to in the water are impacted by things like temperature and light and nutrient availability. So that's going to change the way that their calcium carbonate skeleton forms as well. So this basically happens seasonally. There are growing seasons for coral. So this results in coral basically having rings like a tree. So that allows scientists to date the coral and then gather information for those layers as well. Again, it's like the ice cores on a smaller scale. They'll go down there with little drills, take a core sample of this coral and gather information from that. So they can do different types of chemical analysis on different layers of the coral. They're looking at things like strontium and barium, as well as, oxygen isotopes, carbon isotopes, as well as just looking at the physical properties of those layers to put together lots of different types of information. So again, when we're talking about those oxygen isotopes, that's giving us more temperature proxy data. And they can also look at things more just sort of visually. They can even see like times of stress, coral bleaching events from this proxy data as well. Similar to coral, on land, we've got trees also grow in rings. Probably we've all done that, right? You ever count tree rings as a kid?
Yeah, I feel like you have to do that in some sort of science class at some point. Like I feel like that's part of the American education system.
I think that you are probably right about that. Scientists can actually use that to give good information about the growing season, which in conjunction with all of these other things helps us to sort of paint a picture of climates past. So they will go out to a site, take core samples from trees in a given area, and these things are taken, they are prepared, they're examined under a microscope, they'll take precise measurements of these rings, and different types of trees can then help give scientists different types of information. So back to our friends at NOAA, they talk about how there are some trees that are going to depend heavily on temperature for their growing season. So trees that depend on temperature will have narrow rings during colder periods and wider rings during warmer periods. So better growth during those warmer periods. Trees that depend heavily on moisture during the growing season will have wider rings during rainy periods and narrower rings during dry periods. So these tree rings can be basically a proxy for both temperature and precipitation amounts.
Nature's so cool. I mean, that just also hammers in how important it is to have old growth forests and things like that around. We still learned things from very old living beings on planet Earth. So
okay, one that I knew less about, but found just, again, sort of mind blowing that people can look at this and know this. But pollen, not just an annoying allergen, people, pollen is important climate proxy data. So, fun fact about pollen, I don't know if you knew this as a plant person, Casey. I just assume that you know everything about plants, but
That's a bad
but
assumption.
fun fact about pollen grains apparently have a unique shape depending on what plant they're from. So you can identify plants from their pollen, I guess is the right way to say that. And pollen also apparently has really tough outer walls, which basically means it's really tough to destroy. And that allows it to be preserved in sediment layers at the bottom of lakes and ponds and oceans and so forth. So, hey, we can take more cores of things. Scientists can take cores of sediment, find the pollen grains in that sediment, collect them, observe them under microscope, identify the plants that they are from, and that gives them a picture of the abundance of different types of plants in a given area, in a given time, which again gives you information about what that climate must have been like for that plant, those types of plants to have been there in that relative abundance. So again, that has to do with how much rainfall that area must have been given, how warm or cool that area must have been given. This is super cool. I do not want to be involved in this one. Nope.
It's another one where I was like, wow, the mystery is like one part of that and I would have been satiated. And obviously there's so many parts of it that need to come together to really paint the accurate picture. So it's presumably also like different scientists figuring out and then collaborating a lot of this. But at this point, wow.
Yeah. And that's important to note with all of this. Again, I know we talked about it a little bit with the ice cores, but we're not relying on any one type of proxy data. Obviously, for our oldest measurements, ice cores are a big one, but we are looking at the aggregation of all of these different types of proxy data as we're putting these things together to give us a better and better picture of everything.
Right. And you can look at certain things that are like, compare this to fossils, for example, like the pollen cores remind me of when we look at fossils, how deep they are, can tell us how old they are. Even in amber, when things are trapped within amber, you can find pollen molecules in that as well. And so that can also help us tell what was going on with the wildlife at the same time as the climate, which is really fascinating.
Yes. And helpful as well. Okay. One that I had never ever thought about before was caves. Casey, have you ever done a cave tour?
Yeah.
We used to do the Mark Twain cave a lot when I was a kid. We would drive out to Kansas to visit family and we would go through it. And so we'd go on tours of the Mark Twain caves. Super cool. And I remember they would always stop and talk about the stalactites and the stalagmites and how they form with the water dripping and all of that. They don't talk about how that's involved in the study of climate and climate change, but apparently they are. Also, I learned a new word. Apparently, when you talk about stalactites and stalagmites together, they're called speleotherms.
I like that word.
I do too.
Speleotherms.
Never heard it before. Don't know if I'm pronouncing it correctly, but I thought it was fun. And so these structures are dependent on water for growth, and they are formed from basically mineral deposits that are collected in this water and then left behind over time. So just by looking at the layers of these speleotherms, scientists can determine, again, things like periods of drought or heavy precipitation, depending on what those layers are looking like. And our good friends oxygen isotopes are back here as well, so they can look at that within these structures too. One that I had absolutely not heard of before, but might be my new favorite one, is pack rat middens. Is this something that you're familiar with at all? Do you know what pack rat middens are?
I know that pack rats, and this is where that like phrase like, oh, he's a pack rat comes from, will make like nests, burrows with a bunch of different material from around them. They're very cute.
Mm-hmm.
That's my extent of my knowledge about pack
Well,
rats.
apparently they do that and then they pee all over it. And then that stuff gets crystallized in their urine and is well preserved for a long, long time. So scientists can then collect those things and analyze them and
Thanks,
figure out
pack
things
rats.
about the climate, including using the plant material that's preserved within. So some of those same things that we talk about with pollen, pack rat middens is another source for these things. So determining periods of drought and things like that, if they were finding drought resistant plant material, for example, is one of the things that they can find. But I think, sometimes they might find insect shells and that sort of thing. So they can use all of that as data and do analyses on several different things that might be found in pack rat middens. Who thought of this? Who looked at that and thought, this could really be useful in determining.
I imagine a pack rat scientist, like someone who's just specifically studies pack rats, was at some sort of work conference with some climate scientists and just wanted to talk about how cool pack rats are. And that's how I envision this process happening. Perhaps
Excellent.
it was much more intentional than that, but
Yeah,
I just imagine some cocktails involved. And
I guess I should have maybe found the answer to that question for this podcast, but I did not.
That's a mystery I don't want
yeah,
spoiled.
we can just speculate. That's great. And the last one that I want to mention is I'm just going to talk about it kind of generally. Is just sediment. There's sort of lots of ways I feel like you could divide that up. You could argue that pollen falls under sediment since we're collecting it. But they did find a cool article talking about using ocean sediment as another proxy to estimate carbon dioxide going back millions of years. And basically, this article, which I'll link to, they used two different proxy methods to reconstruct carbon dioxide levels during the last 66 million years. So that one method, they used carbon isotopes in alkanones, and another method using boron isotopes in planktic foraminifera, which are single-celled organisms with calcite shells common in marine cores. There you go. That's the extent that I know about it, but I just wanted to include it because that was a question that I had. You hear that sometimes too, that the amount of carbon dioxide now is the highest that it's been in millions of years. And I was like, okay, well, if our ice cores are only going back 800,000 years, how do we know? Ocean sediment, single-celled organisms that we're collecting carbon isotopes from. It's fascinating and incredible to me, the level that which both, just figuring out these isotopes and then how we're able to measure these things in such a small amount of data. I don't know. I just thought it was really cool. So when the next time you see one of these graphs that goes back however many years, now at least you have some idea. Scientists aren't just pulling this out of nowhere. People have worked long and hard and counted many a pollen grain and analyzed little tiny bubbles in the ice and looked at fossilized shelled organisms and all kinds of different things to bring you the data contained in that graph.
Humans are amazing. I think science is so cool. It's moved so fast, like just a couple hundred years from inventing steam engines to like microscopes that can bounce wavelengths off of molecules in the atmosphere, samples. Like it's so fascinating. It's also good to know all of the ways that we are backing up climate change science. Scientists, activists are calling for pretty large scale changes to the way that our world works. And so we better be doing that with some sort of very credible, solid evidence. And this is being fact checked in a million different ways through so many different cool parts of science, not by the same people, by a bunch of different types of people. Right. So teamwork, making us a little bit smarter.
Yeah, I love it. And there's so much more to learn, and articles were popping up about scientists who are looking at new ways to measure these types of things. And obviously, we still have a lot of questions about how things in the atmosphere works, so those NASA satellites I was talking about, that's one of the things that they're still researching. They're looking at water vapor and what role is that playing in different things, and all of that. One thing I didn't even really talk about either is we mentioned carbon isotopes. Scientists can actually determine where carbon dioxide emissions are coming from to some degree by looking at the different types of carbon isotopes and that type of thing. So there's so much more that we could talk about here, but I do think it is cool and important when we're talking about climate to at least know a little bit about where that data is coming from. So thanks for the discussion, Casey, and stick around. We will be back with our challenge for the week. All right, it is challenge of the week time. I feel like I've been on a little bit of a kick recently with my challenges of just giving you a resource and asking you to learn more, which is not my favorite. Like, I like to have a challenge to where you get out and do something. However, I did talk about one of my goals for this year in general to be learning more. So maybe my challenges are reflective of that. But my challenge for this week is going to be just to learn a little bit more about what we talked about today, or explore a little bit more. NOAA actually has a paleoclimatology data map that you can look at. I'll give you the link to their map. I also found a website that has a map that I feel like is a little more user friendly. That's the same data. They are mapping the data from NOAA. But it's a little bit easier to use. And then when you click on a certain thing, it'll take you back to the NOAA's website. So I might give you that one as well, because to be quite honest, NOAA's map was a little frustrating when I first pulled it up, but it's got a lot of cool things. It has different studies looking at all of the different proxy data things that we've talked about this evening. So you can actually click on it. You can look at studies. You can look at the data, the information that they have there. There's a whole ton of stuff that goes along with that I don't understand at all. But it is kind of cool to see globally where all of these studies are happening, all of the different data points that we have that we're collecting. So that is my challenge for you this week, is just to spend a little time on that. You can look at what types of proxy data have been collected around you, however you want to do it. I think it's kind of cool to see just the mass of data that there is out there, and how spread out it is around the world. So that'll be linked in the show notes for sure. Probably put it out there on our social media as well. Are you already looking at it, Casey?
I will say right now the server will not connect me, but I can see it behind. Like I can't use it, but I can see it. And holy cow, there are so many. Yeah, they have, oh gosh, over a dozen different types of climate proxy data, and it is everywhere. So I'm excited to explore a little bit more on that one.
Awesome. Anything else to add before we go tonight, Casey?
No, but thank you for doing some more climate research stuff. I feel more powerful now.
Oh, good. Well, we love that. All right. If you have questions for us, if you have episode suggestion topics, if you have more climate myths you want us to bust, anything like that, you have lots of different ways that you can get in touch with us. We are on Facebook. You can find us at A Little Greener Podcast. We're on Instagram at A Little Greener Pod. We're on Twitter at A Greener Podcast. And you can email us at alittlegreenerpodcast@gmail.com.
Thanks for listening, everyone. We'll talk to you next week.
Bye.